these A terms are basically like the volume, surface, and radius of the nuclei, right? So A equals volume. Well, A is something related to the volume. A 2/3 is something related to the surface. And predictably, A 1/3 is something relating to a radius or line, okay? These terms here, these A and subscript terms, these are all constants, okay? So AV, oh, sorry, not constants, they are coefficients. So AV, AS, AC, and AA are all coefficients. So they are values that you basically pick from a table. And then N is the number of neutrons, Z is the number of protons, okay? Now we can talk about it. What do you notice? What do you notice about this expression, just in general, okay? So remember when I said, right, that the goal is to get this as large as possible, okay? The goal is to get this as high as possible, yeah? What do you notice about about the majority of this expression?
There's a lot of minuses.
There's a lot of minuses. So this term here, so that term basically serves to reduce the binding energy. It serves to lower it. It's trying to lower it. This term here is trying to lower it. This term here is trying to lower it. To be honest, this term here actually should be plus minus. So depending on your arrangement of protons and neutrons, you can either increase the binding energy or you can lower it some more. The real term that forms most of the positive contribution is this term here. And I'll briefly talk about what they mean. So binding energy, okay? Remember, you are trying to form a nucleus and bind it as tightly as possible. When you bind things tightly, remember, when we talked about potential, where is it? Did I close it? I closed it. Why did I close it? Do you remember that thing about the potentials, the gravitational potentials? Like the closer you get to something, the more energy you radiate away. Okay. It's the same thing here. So you're trying to create a nucleus, and the mere fact that you're bringing stuff together in a volume and you are crushing them together causes energy to radiate away. This is called the volume term. This basically says that however big your volume is, or however many particles that you have in that volume, will give you the bulk of your binding energy. Okay, you're bringing all these things together, you're bringing them close, you're binding them together. This is going to be your positive contribution to the binding energy, right? But now we need to correct. Okay, we need to start doing what I'm going to call our corrections. The first correction is this. Okay, and you know what? As an exercise, I want to see if you can guess. I want to see if you can guess what it may pertain to. So this is called the volume term, right? This volume term just says that because I have all of these particles in a volume, remember, it's the strong nuclear force, right? Do you know what the strong nuclear force is?
Yeah.
That's the glue, yeah? That's the glue that's binding them together. So this term here is saying that because I have all these protons and neutrons in a volume, and I've got all this strong nuclear force glue binding them together, I've got a massive positive contribution to the binding energy, okay? Now, this is called the surface term. And notice how it's a negative, it's reducing the binding energy. Why do you think that is?
Why? So if there's more surface, is it?
It's a pictorial example. So black is neutrons, red is photons. Here's a pictorial example. And think about the fact that there is there is glue, right? So there's strong nuclear force glue trying to act between everything.
So if there's more surface area, there's more glue needed.
Close, like try and narrow it down. Why do we have to correct the volume term using a surface term? What's different between stuff that's stuck in here to stuff that's on the outside here?
So on the inside, you need the stuff together to be all around it, whereas the outside only needs part of it to be.
Yeah. Okay. The nucleons on the inside, they are surrounded by glue, and I'm using glue to, I'm using glue as a placeholder for strong nuclear force.
Yeah.
The nucleons on the inside, they are surrounded by all this glue, so they are tightly bound. Yeah, they are tightly bound. But what about the ones on the surface? They're only being glued that way. They're not being glued from over here. There's no glue out here, so they're not as tightly bound. The surface term basically says that there are nucleons on the surface that are not as tightly bound as the nucleons inside the actual volume of nucleons. Okay, so that's why it's a negative contribution. This term here, so there's another obvious correction now, and hopefully you'll get this one too. This one is called the Coulomb term. How do you spell Coulomb? Coulomb term. This one is called the Coulomb term, and it's to do with the protons. So notice the Z's there. So it's to do with the protons, and notice the A third. So it's basically lines between protons. What do you think this term is talking about? And why do you think it is also a negative contribution? Why do you think it's reducing the binding energy?
Because the amount of energy to keep them charged.
No, you can't. They're protons. They're not fundamental particles, but protons are protons. You're not gonna change the charge of a proton.
Okay. So the radius.
Think about what other forces may be involved here. The strong nuclear force acts between anything that is a nucleon or anything that contains quarks, right? Neutrons contain quarks.
The electromagnetic.
Okay, what about the electromagnetic force?
It take away some of the energy out of it because it's given out electromagnetic.
What is given out electromagnetic force?
The protons.
Okay, and like what are they essentially doing to each other?
They're repelling each other.
They're repelling each other, right? Every single proton is repelling another proton along a line, right? So this, even though they are bound by strong nuclear force, it doesn't matter the distance. This proton on the outside, for example, this proton on the outside here is going to be repelling this proton on the inside. That proton there is going to be repelling this proton all the way over here. That proton there is going to be repelling this proton here. That proton there is going to be repelling that proton there. There is repulsion in lines between every single proton within the volume. Okay. Yes, the strong nuclear force is strong enough to keep it all together regardless, but the mere fact that there is repulsion between every single proton unbinds. It tries to unbind the atom or the nucleus, right? So that's why the Coulomb term reduces the binding energy. I'm not going to bother talk about the rest because to talk about the rest, you need to know a little bit about